Hey, how's it going, everybody? We are here at the beginning of week 12. We're going to be talking about chapter 10 this week, which is going to discuss all of our two sample hypothesis tests and confidence intervals. In the previous 2 weeks, we saw our one sample hypothesis tests and our one sample confidence intervals. So this week, we're just going to kind of upgrade those things that we've already seen to be able to discuss comparisons between two samples rather than just an analysis of one sample. Uh, Briefly, let's talk about some of the questions that we expect to be able to answer by the end of this week here. One question we might want to ask is, are men taller than women? Are Californians more likely to go to college than Coloradans? And does a certain diet pill result in weight loss? So let's very briefly talk about what comparison we're making here. What are the two samples that we're collecting? And kind of set ourselves up for what we're going to expect to see for this week. So when we talk are men taller than women, it looks like we're comparing their heights. So in this case here, it seems like the appropriate way to measure this would be to collect a sample of men, collect a sample of women, and compare the averages from these samples. So let's say here that we're going to compare two averages. And the second question here, are Californians more likely to go to college than Coloradans? You either go to college or you don't. That's a binomially distributed variable. It seems like we're discussing proportions of Coloradans and Californians that go to college. So in this case, it seems like the appropriate way to measure, to analyze this question would be to take a sample of Californians, a sample of Coloradans, and determine the proportion of respondents that say, yes, I go to college or not. So it looks like here we are comparing two proportions. Finally, the third bullet point is our one sort of new scenario this week here. This is a little bit of a sneakier one. Does a certain diet pill result in weight loss? And the question that I should be asking you right now is, what are the two samples that we're comparing in this case? How is this a two sample test? How are we going to measure weight loss here? And the thing that makes this one a little bit different than the other questions that we're asking is that the samples that we're going to draw, samples, plural, is going to be from the same group of people. If you want to determine if a diet pill works, then the only real way to measure that is to measure a group of people's weight, give them the diet pill, and then at some time later measure their weight a second time and see if they did in fact lose weight. So the thing that's a little bit different about this third bullet point right here is that in this case, we are really comparing a before and after. And the thing that you should notice here is that we're really pulling from the same group of people in each case. And that's going to mean that we are going to think about this one a little bit differently right here. So I'm just going to say here, comparing before and after. We'll talk about this distinction a little bit more in a minute here. Officially, this is going to come up in the next video when we're going to actually look at this example right here, but I want to kind of lay out everything that we're going to see this week kind of up front here. So I do want to kind of identify that this guy seems a little bit different than what we've seen before here. And we'll talk a little bit more detail about that today, a lot more detail about that in the next video. I guess I could... So in our previous weeks here, was that in week 9, week 10, we saw 3 hypothesis testing scenarios associated with one sample test, right? So this is what we'd seen before with our one sample test. We saw that we could perform hypothesis tests and compute confidence intervals for a population mean when sigma is known. I want to be specific here. Or if we didn't know the standard deviation, then we could use the t-distribution to help us compute our hypothesis test confidence interval information there. And finally, if we're looking to perform a hypothesis test or compute a confidence interval associated with a population proportion, we saw that we always use our z-distribution to help us with our calculations there. So what we want to do is see how are our requirements from before comparing to our requirements now associated with each of the tests that we're going to do. We want to make similar distinctions here with our two sample tests. The breakdown is very similar, and it's going to primarily depend on the size of each of the samples that we've collected. You should notice that now we have not just an n for a sample size, but an n1 and an n2, because in each of our scenarios now, these are all of our two sample tests. We're collecting two different samples. We're going to have two different sample sizes, two different sample averages, two different either population or sample standard deviations, things like that. So what we can see here from these 3 bullet points for our breakdown for our 2 sample tests is that if our sample size is at least 30 collectively between the 2 samples that we take, then we're going to be using our z distribution to compute our probabilities. And in fact, even if our collective sample size is less than 30 between our 2 groups, we will still use the z distribution if we knew our population standard deviations, right? This says if you know sigma, you can still stick it out with z. The only situation in which we're going to use a t-distribution to compute our probabilities associated with our 2 sample test is if we both have a collectively small sample size, the sum of the 2 sample sizes is less than 30, and if we don't know the population standard deviations. If we only know the sample standard deviations, S1 and S2, and if the 2 samples are very small, in that case, we're going to have to stick it out with a t-test here. Otherwise, we're going to get to use the z-test, which is going to turn out to be quite a bit easier for us in these scenarios here. So why do I say it's going to be easier for us to do our z-test information rather than our t-test information? Let's talk about this one real quickly. What we've seen in our previous weeks is that when we want to compute any probabilities associated with a t-distribution, then the extra piece of information that the t-distribution requires you to know is a number of degrees of freedom associated with the sample that was drawn. This was a really, really simple calculation for us to do. Our degrees of freedom for the t-distribution, we've just computed as 1 fewer than the sample size, just n minus 1. It's not going to get easier than that, right? We're going to see a little bit tougher of a calculation to get our degrees of freedom here associated with the t-distribution when we have a 2 sample test. So I'm going to show you this formula here. We will use this formula. It's pretty gross, but it's also just a quick trip to a calculator here. So unfortunately, our degree of freedom calculation here gets a little bit tougher when we talk about the t-distribution. But a couple good things to notice. One, you should notice that out of all the terms that are sitting out here, all we have is the 2 sample sizes, N1 and N2, and the 2 sample standard deviations, S1 and S2. Those are the only 4 pieces of information that we have floating out in this computation out here. So while this is a kind of a bummer formula to help us determine the degrees of freedom associated with a small sample, 2 sample test here, it also is just a trip to your calculator. You certainly should be just looking this guy up every time you need to use it and using your calculator to help you make calculations. So it is a careful trip that we need to make to our calculator, but it's still just a calculator trip nonetheless. So we'll look at one t distribution example today, and we'll come back to this formula and compute a degree of freedom associated with this. We'll see it. It's just a little extra lump to get over here in some of our hypothesis test confidence interval scenarios here. And before we get into our examples here today, I do want to point out what this one new scenario is, right? So I mentioned this up above that before and after seems a little bit different than everything else that we've seen. So let's talk a little bit more about this. Again, we're going to hit this example in particular in the next video, but I do want to kind of present everything to you that we're going to end up seeing this chapter right away here. When we're trying to analyze the distinction between 2 samples, we need to know if the data that was drawn for the first sample is independent or not from the data that was collected associated with the second sample. So let's make a distinction between these 2 scenarios, independent versus dependent, with 2 examples. In the paragraph that's on the left, we're discussing the average salary of people with PhDs versus people without PhDs. We're asking, do people with PhDs make more money? The way that we would measure this is we would collect a sample of people with PhDs, 25 of them apparently, find their average salary, collect a sample of 20 people without PhDs, find their average salary, and we can make their comparison, right? The very important thing to notice here is that the data that we're going to collect for one group is going to have no bearing whatsoever on the data we collect from another group. It's not like we're going to collect a sample of some very, very highly paid people with PhDs, and that will somehow influence the dollar amounts that we end up observing from the people without PhDs. These are 2 separate groups completely. We're not expecting to see any direct relationship between what we collected in the first sample and what we collected in the second sample. So here I would say these samples are independent of one another. Right? On the other hand, if we're talking about weight loss, the example that we saw up above, if we'd like to determine if a weight loss drug works, we're going to weigh 40 people initially. Then we're going to give them a bottle of weight loss pills and instructions on diet exercise. 6 weeks later, we're going to weigh the people a second time. The important thing to notice here is that because we're collecting like a before and after sample, we're really collecting data from the same people two different times. That means that there is a relationship between the data that we collected the first time and the data that we collected the second time. For example, if a person begins this weight loss trial weighing 500 pounds, I certainly expect that same person to still be very much overweight at the end of a 6 week trial period here. Even if this guy still has great success losing weight, he's still going to be heavily overweight by the end of the trial. On the other hand, if a person begins this trial already underweight, I expect them to end the trial still underweight, right? Stuff like that. I have an idea of the relationship between what the early value is in the first sample and what the late value is in the second sample. There is dependence of values here. If I know that I sampled only very heavy people in the first trial, in the first sample, excuse me, then I expect to again get a sample of only very heavy people in the second trial that's out there. So in this case, we do have a dependence between each of the two samples, and it's because they're really the same group of people. Um, so let me just say these samples are dependent on one another. All right. So in general, if we're collecting a sample from the same group of people, we're going to expect to see that these are related samples to each other. We know information about what to expect for the later sample because of the information that we collected from the earlier sample out there. So when we have a dependence between samples, we're going to want to deal with this a slightly different way than our independent samples that are out there. So again, we're going to see this example in the next video, but I just want to kind of highlight this difference to you that when we collect two samples, it matters that we stop and ask ourselves, is there some relationship between these two samples, or was this just two different samples that got collected out there? And we can see that distinction in these two example scenarios that we're looking at right here. All right. So that what that means to us is that in total there are 4 different two-sample tests that we're interested in being able to perform associated with this week's content here. We've got the 3 that we have seen from before, our two-sample tests for means and our two-sample tests for proportions. But the one new one that we have now in here is if our samples are dependent on one another, then we will perform what is referred to as a matched pairs test. Because in this case, I have these matched pairs. The first person in each sample in the weight loss example above is actually the same person, right? It's not just that sample observation number 1 and sample 2 observation number 1 are from 2 different samples. They're literally the same human being that we collected the data from there. And so those are referred to as a matched pairs test. And also, I just kind of want to point out, it doesn't necessarily have to be like literally the same person involved for us to say that these are dependent. In some studies, we want to look at things like, do husbands and wives tend to vote for the same political party? In that case, there is dependence, because if we collect a sample of all the husbands first and then all of the wives later, we should expect to see that the wives' responses are more likely to match that of their husbands than not. It's typically the case that husband and wife couples often have similar political leanings out there. So in that case, even though we're not collecting data from the same person, there's still information that we know of what to expect for the second sample based on what we saw for the first sample. There is dependency in there because being married is a very close relationship. It allows us to, it gives us some more predictive ability that we wouldn't have otherwise had if these were truly 2 separate independent samples that are out there. So again, we see the same scenarios here, a 2-sample test for a difference in population means, if the standard deviation is known, z-test, 2-sample test for difference in population means, a t-test where the standard deviation is not known and we have to use the sample standard deviation. We have our matched pairs test for the difference in population means with dependent samples. That's where there's a dependency from one sample to the other. In that case, we'll do our matched pairs test. We'll talk about that guy next video. We also have our 2-sample test for difference in proportions. Are Coloradans more likely to go to college than Californians? Stuff like that. We'll also look at our proportions. The second 2 bullet points will be next video. The first 2 bullet points that you're looking at right here, we'll do our examples for these guys here today. So we want to be able to perform these hypothesis test confidence intervals here. So let's go ahead and take a look at how these things are going to compare with what we've already seen, and then we'll go ahead and hit our examples here. So the good news for us is that generally speaking, the four steps of the hypothesis test haven't changed at all. Just a little bit of the computation that we're going to do is going to change. So let's go ahead and look at what parts of our hypothesis test are a little bit different here. But overall, the really big takeaway that you should be seeing here is that not much is really changing. The structure is of our approach is the exact same here. We're just filling in the blanks with some slightly different things because we have two samples instead of one. So we just want to update our approach to deal with that. So we need to know how to form our hypotheses and compute our test statistics associated with these scenarios. The computing of the p-value and arriving at our conclusions are going to be pretty much the exact same. We just need to update a couple pieces of this guy here. So let's talk about our hypotheses associated with two sample tests. And so our null hypothesis, this is still our statement of no change. Oop. Which now is probably better interpreted as our statement of no difference. So what that means to me is that in all of these cases where we're saying, are men taller than women, the null hypothesis will say no. Do Coloradans go to college at a higher rate than Californians? Our null hypothesis is going to say no. It's the statement of there is no difference between the two groups. Did this group of people experience weight loss? Was there a change in weight? The answer will be no. There's no difference in their weight after compared to before. Those are all of our null hypothesis statements here. So some null hypothesis statements that we might expect to see then is that our null hypothesis might state that the average value for group 1 is the same. There's no difference as the average value for group 2. You should notice that this is the exact same thing. I'm going to just do a little bit of algebra right here. Algebraically speaking, I could look at this equation right here and I could subtract one of these terms over to the other side. So this is sort of verbalizes to me as saying the average of group 1 is the same as the average of group 2. Just doing a little bit of algebra, I could rephrase this as saying the difference in average between group 1 and group 2 is 0. So notice that this is just me algebraically subtracting one term over to the other side right there. These two statements are the exact same statement right here. There's no real difference in this. So we again might see for our null hypothesis here that our proportion for group 1 is the same as the proportion for group 2, or you might go ahead and write this as the proportion for group 1 minus the proportion for group 2 is 0. These are really the same way to say the same information right here. So I don't care if you reference your null hypotheses as equal signs over here with 1 on either side of the equal sign, or the difference between the two is equal to 0. Those are really expressing the exact same idea. So these are our typical null hypotheses associated with these tests here. Our alternative hypotheses, we might expect to see things like our mu1 is maybe greater than our mu2, or our p1 is less than our p2, things like that, right? So we're still going to get our greater thans, our less thans here for our alternative hypotheses, but recognize that we're always making our comparisons between two groups. So the very important thing that you need to realize is that if you are talking about a hypothesis test for a two-sample test, then you have to reference two different population parameters. We're comparing, is the population average the same for these two groups or not? Is the population proportion the same for these two groups or not? And again, just notice that you have the option of either kind of thinking about this as saying group 1 is the same as group 2. That's what these two guys look like to me. Or as saying the difference between group 1 and group 2 is 0. There is no difference between group 1 and group 2. So again, this setups on the left are identical to the setups on the right. It just is a matter of preference right there for how you indicate those. And you should expect for your alternative hypotheses here, again, to include your less thans, your greater thans. or equal to's as well right there. So it's still equal signs with the nulls. It's still less thans and greater thans for the alternatives out here. Just be sure that you're referencing both of the populations that we want to discuss in your null and alternative hypotheses. The other thing that's going to change here a little bit is how we compute our test statistic, and that's because we have information about two samples now rather than information about one sample. So let's go ahead and see how this is updated. Today we're just talking about means, so that's all I'm going to discuss right here. Next video we'll talk about proportions and we'll see our computation that's associated with that, but the update will be very similar to what we're going to see today. So in general, what we've been seeing is things like how are individuals distributed, where we started with things where an individual X was normally distributed, maybe with a mu sigma distribution right there. Then we said, okay, we're not just interested in individuals from a normally distributed sample. Maybe now we're talking about individuals from any distribution, and we're talking about how are their averages distributed if we take them n at a time. And here's where we said, well, if we want to see how the averages are distributed in groups of n at a time, then the central limit theorem told us those should be normal regardless of the underlying distribution of this guy up here. This did not need to be normal for us to find that this is going to be normal down here. We found that our group average should still be the same, whether we're looking at groups of 30 people at a time or just one person at a time. The overall average should be the same. But what we're going to see is that it's much harder for groups to deviate from the mean than it is for individuals to deviate from the mean. And so we're going to see that as our sample size gets bigger, our standard error term gets smaller. This is our standard error here. All right, that's our sigma over root n. And our big takeaway here is that n is a division term down there, because as n gets larger and larger, the value of this fraction gets smaller and smaller, representing that idea that as a group becomes bigger and bigger, it's harder and harder for it to deviate from what's happening on average. So the important thing that we need to see here now is the next line here. How are the average differences between two groups of size n1 and n2 distributed? So what we're really looking to see is how are the sample averages between two groups distributed? So I want to see what's the difference between the average value for my two groups. We will see that this is normally distributed. The average value is going to be exactly the difference in average values as proposed by the null hypothesis. And we're going to get a standard error term that's going to feel a lot like this guy right here. And I want to kind of talk about why you should vaguely believe this equation that I'm just handing you right now. So it looks like our standard error for z is going to be that square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So here's the thing I'm kind of seeing with this guy. Notice that in the numerator we have a squared term, and on the outside we have a square root. Now, it is not the case, by the way, I'm just going to write this over here. It is not, I'll just write it over here. It is not the case that the square root of a squared plus b squared, this is not equal to a plus b, right? You cannot just take a square root by individually square rooting each of the terms. That's not true right there. But hopefully you can see that there's at least some relationship here, that we're talking about these square roots of sigma squared, so that should just be like sigma. And we just have n on the bottom, so that's like square root of n down there, right? So this should look to you sort of like sigma 1 over root n1 plus sigma 2 over root n2, which is sort of like just adding together two standard error terms. Now, we get this kind of algebra inconsistency here where that's not quite true because you can't individually participate in that square root over addition right there. That's not really how that works out. But hopefully you can kind of see this, like, I don't know, like squint your eyes and see this in fuzzy terms right here. Hopefully this feels to you sort of like the addition of two of these terms right here, just one from each sample. And again, this rule right here tells us that it's not exactly the case right there, but it should feel similar to you in that case right there. You should notice that in the event that we're going to be looking at our t distribution, if we have those small sample sizes there, then we're going to be using our t distribution, and in that case, we're just going to be using S instead of sigma, right? So we're just making that same swap right there that we normally make, just using S instead of sigma, using the t distribution instead of the z distribution there. So these will be the standard error terms that we will interpret as like a standard deviation term associated with our computations. The good news for you is that this is really the only thing that's different in our hypothesis testing confidence intervals from the previous weeks. We just need an updated way to discuss our hypotheses, to discuss two tests, two population parameters, and we needed a way to update our calculations to perform our z and t, to compute our test statistics here. Even computing the p-values associated with these won't have changed. So let's go ahead and look at our examples here for today. We're going to go ahead and look at the one that I kind of proposed earlier. Is there a difference in salaries between people with PhDs and people without PhDs here? So let's go ahead and perform my hypothesis test and compute a confidence interval. So I'm going to talk through this example here so that I can scroll away from it. This is exactly what I proposed before. I just actually gave some information here. We would like to determine if people with PhDs make more money than people without PhDs. We sample 25 people without PhDs and find that their average income is $41,000 per year with a standard deviation of $15,000. We sample 20 people with PhDs and find their average income is $59,000 per year with a standard deviation of 14,000. First, let's perform a significance test, a hypothesis test with a significance level of alpha equal 0.01 to determine if people with PhDs make more money than people without PhDs. Then after that, let's form a 90% confidence interval for the average amount more made by PhDs than non-PhDs. So those will be our two tasks here, one hypothesis test, one confidence interval. So let's start off with this hypothesis test statement here. And by the way, I guess before I get started here, I kind of want to identify sort of my two groups here. And the important thing to do here is to recognize that you've now got to keep two groups of people, or two groups, not necessarily people, distinct here. It's typically the case to number our labels, our subscripts as ones and twos. But like if you have things like male and female, use M and F. That's just going to make it easy for you to not get confused there. And maybe I'll do that in our second example here. I'm not going to do subscripts of PhD and non-PhD, so I'm just going to call these groups 1 and 2 here. So what I'm seeing right here is I want to identify the information that we're seeing. So here I'm going to see N1, this is the sample size for the with PhD, 25 without PhDs. So that says to me my N2 is 25. That was 25 without PhDs. 20 people with PhDs were sampled. So that's going to be my sample size for group 1. It looks like we were given a sample average for the with PhD grouping. So the with PhDs, their average income was $59,000 per year. And by the way, I think I'm just going to abbreviate this all to being measured in thousands here to save a little bit of room. And our sample for the people without PhDs was $41,000 per year. And finally, it looks like we were given some standard deviations here. And notice that in this case here, it does look like we were given these sample standard deviations here, but because our collective sample size is greater than 30, we're still going to be okay to use a z distribution to compute our probabilities here. It's going to save us a little bit of effort here. So I do want to identify that these are S1 and S2, but I will say here that because N1 plus N2 is greater than 30, we're going to be okay to use a z distribution to compute our information. And that's good for us because we don't want to have to compute that degree of freedom term for the t distribution that we saw up above up there. So it looks like our standard deviation here, I'm seeing that 15,000 is the standard deviation for the grouping without PhDs, and I'm seeing 14,000 is the standard deviation for the group with PhDs right there. So I've collected all my information, and again, don't let yourself be confused. If you use generic labels like a 1 and a 2, then you should write down what your label is. It should be easily understood by anybody that's reading your work what your two groups are. And so if you use generic labels like 1 and 2, then you need to write down what group is 1 and what group is 2. Again, if you're talking about your two groups being male and female, then I would just use M and N, or M and F as my two subscripts instead of 1 and 2, and then it's obvious what's going on and you don't need to explain it any further. But if you're going to use generic labels, then you need to write down what your label means. Group 1, PhD. Group 2, non-PhD. So let's now form our hypotheses associated with this test here. Our null hypothesis is always our statement of no change or no difference. So here I'd be saying that there is no difference in the average salaries of people with and without PhDs. So that would be to say the average salary of people with PhDs is the same as the average salaries of the people without PhDs right there. It's supposed to be a 2. And I will just say right here, it's totally fine if you say this our subtraction version instead. This is, in a sense, this is almost truly our statement of no difference because this is the difference and the difference is none right there, right? So either way that you want to phrase that is acceptable. So let's reread the problem here. We would like to determine if people with PhDs make more money than people without PhDs. So it seems like what we think is happening, what we're suspicious here, is that the PhD group is going to make more than the non-PhD group. So it seems like we think that group 1, the PhD group, makes more than group 2, the non-PhD group. So it seems to me like the appropriate direction of my test here is that mu1 should be larger than mu2. And again, notice that it's acceptable to phrase this in a subtraction sense instead, if you would like. Mu1 minus mu2 is equal to 0, or excuse me, is greater than 0 right there. Greater than is the important part right there. So I just did a little bit of subtraction. Again, I subtracted that group 2 over. But again, here we're saying that we think that the difference is positive. If we do subtraction of the non-PhDs from the PhDs right there. I think that this one's slightly less good for interpretation when we do our alternatives. I think in the alternatives, it's best to just do the direct comparison greater than or less than. But again, these are mathematically speaking identical sets of statements right here, the ones on the left and the ones on the right. We can now go ahead and compute our associated test statistic associated with this test here. And recognize now that we're going to continue to make the same sort of like upgrades to our formula. Right? So it used to be our very first computation for z, we did for a one sample, we did x minus mu over sigma. Then we upgraded our computation to be x bar minus mu over sigma over root n. Now what we're going to do for our two sample tests, this is our guy for us down here today. We're going to take this exact same structure as we've been seeing before. We're going to take our sample information minus our population parameter information according to our null hypothesis divided by our standard error. So in this case, this is going to look to us like x1 bar minus x2 bar. That's our sample information minus mu1 minus mu2. That's our parameter information, all divided by our standard error information over here. And this will be our S1 squared over N1 plus S2 squared over N2. So this is the guy for us here. And let me just say, so I just want to remind us here, since we have that our two samples collectively are greater in size than 30 overall, that sort of says to us, listen, it's going to be acceptable for us to use the z distribution to compute our probabilities. We're going to get essentially the exact same results as if we were to use a t distribution here. So while it is true that I'm calling these s's because those are the sample standard deviation, I'm still going to use a z distribution to compute my probabilities because my two sample sizes are larger collectively than 30. So let's go ahead and throw this stuff into the formula here and see what we're going to get. So it looks like to us here, for our z computation, I'm seeing here x1 minus x2. Well, I've got all my information up here. x1 minus x2, that's our 59,000 minus 41. You should notice here that mu1 minus mu2, it's almost always the case in a two-sample test that this is going to be equal to 0. In most all two-sample scenarios, our statement of no difference here is always going to look like this, unless we have some previously known difference. So notice that it might be something like Somebody claims that men are on average 1 inch taller than women. In that case, our null hypothesis statement would be that the difference is equal to 1 instead of equal to 0. But it's pretty typical in lots of two sample cases that we're looking to say, is there a difference or isn't there? And if we're saying that there's no difference, then mu1 minus mu2 will always be 0 right there. So that's a pretty typical thing. Doesn't always happen, but very, very typical for that second grouping to just always be 0. Now we've got our somewhat gross term down here on the bottom, but it's really not that bad. So we're going to get a square root here. I've got my, oh, and by the way, notice another kind of nice thing that's happening down here underneath the square root. Because this is addition underneath this thing, it doesn't matter if you do, a plus b or b plus a is the same thing. So it doesn't even matter if you sort of get your order correct down there on the bottom. It's addition. Addition works the same both directions. So you don't have to worry too much about like group 1 and group 2 as long as you're not like mix matching the group 1, group 2 information across numerator denominator. It's all good. I'm going to try and keep mine in order right here. It looks like we had a standard deviation for group 1 of $14,000. I'll need to square that. Divided by the sample size from group 1 was 20. Plus, I've got the standard deviation from group 2 was 15. We'll need to square that. Divided by the sample size from group 2, which is 25. And we'll end up taking the square root of that entire thing right here. So I'll do at least one line of intermediary work right here. It looks like in total, our entire numerator is 18. It's really referencing 18,000 right there. And down here in the denominator, we can go ahead and compute our standard error term. So I'm getting, let's see here, 14 squared divided by 20. Plus 15 squared divided by 25. And that's giving me 18.8 underneath the square root. And so in total, I'm going to get here 4.151. All right, so let's remind ourselves of where we are at with kind of interpreting this value here. Remember that what we just did in our computation is the thing that we always do in our computation, which is that we assumed that the null hypothesis was correct, right? That was us using this value of 0 right here. We assumed the null hypothesis was true to make this computation. So what this computation, this z value right here says to me is this. This says, if it really is true that there's no difference in PhD salaries and non-PhD salaries, then this sample that we just took, these two samples that we just took represent a deviation from the mean of no difference by over 4 standard deviations, right? And this is saying to us, if it really is true that there's no difference in salary between PhD and non-PhD people, then these two samples that we just drew would represent samples that are in total more than 4 standard deviations from the average expected result. That's a lot of standard deviations away, more than 4 standard deviations away from the mean here. So what I'm expecting is that this probably represents a pretty dang rare event right here. This is saying to me, I'm going to probably end up deciding that this is so unlikely that it's actually probably the case that the null hypothesis wasn't true, rather than just believing that this just happened to be a more than 4 standard deviation away from average event right there. Right? This is a very unlikely event, more than 4 standard deviations away from the mean. So we want to compute our p-value here. You should notice, by the way, that we had a greater than associated with our alternative hypothesis, and therefore we are going to have a upper-tailed test. So let me just say here, our HA of mu1 is greater than mu2 says we want the upper tail. That's what the greater than is telling me here. So in my z distribution out here, we've got our normal distribution. And I'm looking at the z-axis here. So we're really all the way out like at that value right there, right? There's very little area right there. So this is my value of z equals 1 or 4.151. That little area right there, area equals the p-value. remember that our p-value is measuring what's the probability that we would take another sample, or another two samples in this case, and see an event that's at least as extreme as the one that we've already seen. So that would be seeing an event that has at least 4.151 standard deviations above average. It's going to be a very small probability here. So we can compute this probability, the probability that z is greater than 4.151. I'm going to do this as 1 minus, and this should be our norm.dist. I'll give it the 4.151, 0 for the mean, 1 for the standard deviation, true for the cumulative, and this should be giving me our overall p-value here. So let's go to Excel and do exactly that. I'm going to do my equals. I'm doing 1 minus because we're interested in upper tail, not a lower tail. Norm.dist. Norm.dist, my value of interest is 4.151. My mean is 0. My standard deviation is 1. And that's because we're in a z distribution. That's always a 0, 1 for the z distribution. We're always doing cumulative here. And you can see it's giving me one of these e values here. Remember that you are expected to be able to interpret this. This is just a little bit of scientific notation telling you to shuffle some decimal places. This says shuffle your decimal place 5 units to the left. So that's going to give me a 0.1234 of those zeros, 1655. So here's my p-value here. Notice I took the decimal place that was 1 place to the right of the 1, and I moved it 1, 2, 3, 4, 5 places to the left. That's what the -5 is telling me on the end of that guy right there. So this is a crazy small p-value. Notice that we could move the p-value to 2 places back to the right to get this as a percentage. And notice that what that tells us is it tells us there is a 0.0016% chance that we would see observations like this if the null hypothesis were true. That's such a small probability of seeing outcomes like this that I no longer think the null hypothesis is true. This is such a rare event. It seems much more likely to me that the null hypothesis is false than that we just got an event that occurs 0.0016% of the time. So here, my conclusion will state at the, let's see here, at the alpha equals 0.01 level of significance, our data are significant. That means that we did have a p-value less than alpha. So we reject the null hypothesis and conclude that people with PhDs do make more money than people without PhDs on average. Right? So we're talking about their averages. That's not to say every person with a PhD makes more money than every person without a PhD. We're saying that on average, people with PhDs do make more money than people without PhDs based on this data associated with these 2 samples right here. All right. So again, this is a crazy rare event. And again, I want to go back and re-emphasize what's happening with the hypothesis test. I think this is the thing that's sort of lost on people in doing these hypothesis tests. We always perform the calculations of our hypothesis test based on the assumption that the null hypothesis is true, even though we kind of think it isn't. This assumption that the null hypothesis is true led us to a crazy statement. It said, listen, then if the null hypothesis is true, then this sample that we drew only occurs 0.00166% of the time. That's like 1 in 16,000 or something like that, right? Am I exaggerating right there? 1 in 16,000? Yeah. No, it's like 1 in 6,000, right? Yeah. So this is like a either this was like a 1 in 6,000 sample that we drew right there, crazy unlikely, or the null hypothesis is wrong. Which one do we think it is? Well, this is such an unlikely sample to draw for just a single sample that I don't really think that this is that rare of an event. That seems so unlikely to me that we would get a sample that's that unusual. Therefore, we're going to go back and say, listen, I think our upfront hypothesis was wrong. We assumed that the null was true, but if the null is true, then we just saw a 1 in 6,000 event, and I don't think that that is something that's reasonable for us to see. That's such a rare event that I actually think that it must have been the case that the null hypothesis was false. So we're going to reject the null hypothesis because of the fact that this was much more rare than our rareness cutoff. Our alpha value is 0.01. That said to us, if we see any event more rare than just a 1% chance, that's going to be rare enough for us to change our minds. And we saw something that was more rare than a 1% chance, and so we changed our minds. We no longer think the null hypothesis is true. We now believe that the alternative is true, that people with PhDs make more than those without. All right. So before we move on to example 2, we also want to compute a confidence interval that's associated with this guy here. We're also, right, isn't that what I said? Form a 90% confidence interval for the average amount more made by PhDs than non-PhDs. So for our confidence interval then, so we want to form a 90% confidence interval. So first of all, let's find our z star value. Remember that if we're looking for our 90% confidence interval, then 90% of our probability, we can draw a diagram of the middle 90%. This says that 10% are in the upper and lower tails, so that leaves 5% in this tail and 5% in this tail. Our critical values here, this will be my z star, is always located at the upper bound of that middle percent. And we should notice here that 95% of the area is to the left of z star. So our z star should be norm.inv of 0.95. And I think it still wants true in here, right? Is that the case? Sometimes I forget what it's looking for here. So equals norm.inv, and it wants the probability, that's 0.95. Oh, it does want the mean and standard deviation. Oh, and that's it right there. I was wrong with this right here. All right. And that's going to tell me that our z star in this case going to be 1.64, and I'll round this to 3 decimal places, 1.645. So what we saw before in our one sample case was we saw our point estimate was x bar plus or minus our confidence level z star times our standard error. Now in our 2 sample case, we're just going to upgrade this to reflect the same things that we just saw in our test statistic computation from before. We're going to see our, oh gosh. So in our 2 sample case here, instead of looking at 1 sample, we know that we're looking at the difference between 2 samples. That's still our estimate for mu1 minus mu2 is x bar 1 minus x bar 2. We're still interested in multiplying by the number of standard deviations that are associated with that 90% confidence. That's still going to be our z star. You should just notice that our standard error term has changed, right? Instead of doing s over root n or sigma over root n, we've got our entire square root term, the square root of s1 squared over n1 plus s2 squared over n2, right? So we're going to use that guy here as our standard error term. So we're going to get our s1 squared over n1 plus s2 squared over n2. And now we can go ahead and compute our confidence intervals associated with this guy. So let's keep moving this stuff out of the way. So we've got a little bit of room right here. And so notice here, again, I tried to encourage you to see this before. Our structure of what we're doing hasn't really changed. Conceptually speaking, we're still doing the same things. We just need to update our calculations to reflect that here. So again, we're kind of revisiting our values from before. X1 minus X2, I'm trying to remember what that was from before. X1 minus X2, that was 18. That was our 59 minus 41. Plus or minus our Z star value is the 1.645. We're taking the square root of, and I guess I can just pull this information from here. Our PhD people were 14 for their standard deviation over 20 plus our 15 squared over 25. And actually recognize the good news here. I've already computed what this entire standard error term is underneath the square root. It's square root of 18.8. So I'm going to reuse that calculation here. So I'm going to get here 18 plus or minus 1.645. And this is the square root of 18.8. And so 18 plus or minus, I'm going to go to my calculator again here. I got the square root of 18.8 times 1.645, and that's going to tell me 7.133. Like that. 133. I'll round to 3 decimal places right there. And so now we're able to form our confidence interval, our 90% confidence interval here. So I can do my little bit of addition subtraction right here. It looks like for our lower bound here, this will be 18 minus 7.133 and 18 plus 7.133. And these will be giving me values of 10.867 and 25.133. And so I could state my confidence interval as 10 point, okay, here's what I should do now. I'm going to switch these to commas since we're representing tens of thousands. Don't erase everything on me, please. Thank you. So $10,867 up to $25,133. Or, as you guys have been seeing, we could be writing this as 10,867 is less than mu1 minus mu2 is less than 25,133. So in words now, we can form our conclusion for our confidence interval here. We are 90% confident at the true average. Let's see here. Sorry. So these are a little bit tougher to phrase when we're comparing two samples here. So let's be a little bit more careful here. We are 90% confident that that people with PhDs make on average between 10,600 or $867 and $25,133 more than people without PhDs. That's their average salary right there, right? So what we've done now is based on this data, we have a 90% confidence interval that says about $10,000 to $25,000 more per year is what we should be anticipating people with PhDs making than people without PhDs. And again, it's just on average. This is not going to be true for every person with and without a PhD here, but this says from our samples information, from only these 45 people that we've looked at this information for, we can come up with this interval. You should notice that this is a pretty wide interval. And a thing that I think to myself is when it's a 90% confidence interval, that's not very confident. So that should result in a pretty narrow window. But our sample sizes here were very small. Since we collected so little data, we're not going to see a very wide margin of error right here. So small sample sizes lead to big confidence intervals, which aren't very good. We would like confidence intervals that are very narrow, so we know for sure where this population parameter lives, our estimate for that guy. And we're getting kind of less good information here because there was only 45 people that were sampled overall, right? But we can still compute a confidence interval and we can still interpret it pretty much the same as we were interpreting them before. And when I say the same, by the way, I want to maybe say to you guys, you should really read your conclusion sentences out loud to yourself. What you will realize is that some of you are writing down some insane things, and you won't notice how crazy it sounds what you wrote until you say it out loud to yourself. So I would strongly encourage you in all of your conclusions, especially with the two sample tests, because they just get weirder to verbalize. Write down your conclusion and then literally say it out loud. Pretend that you're going to say this to a random person on the street. Will they think that you're a lunatic? Probably because you're quoting stats conclusions to them. But it's hard to phrase these well. You saw me just kind of like go back and rethink about how I wanted to verbalize this. Recognize that you want to kind of stop and be careful about how you verbalize these. They just get a little bit awkward when we have these two sample scenarios here. All right? So let's look at one more sample or one more example here today, one more scenario. And in this case here, we'll see a little bit smaller sample sizes. We'll look at a t distribution instead of a z distribution here. So let me just move all this down. Well, it doesn't matter that much. Okay, I've lost my keyboard. Oh, is that not going to come back? Okay. So I've lost my keyboard. I don't have any way to type now for the rest of this thing, so I'll do my best, but I might need to kind of freehand write some things here that I would otherwise be typing. So in scenario two, we want to compare the number of hours that boys and girls spend playing sports. It is believed that boys and girls aged 7 to 11 spend equal time playing sports each day. The study is done to test this. The study is going to sample 9 girls and 16 boys, and we're going to find our average and standard. Oh, apparently it's writing now. My good old 15. Oh, but we can't backspace against it. Oh, who knows? Maybe I have a keyboard. Maybe I don't know. So this samples, we got 9 girls, 16 boys. We've got their sample size. We've got their average. We've got their sample standard deviation. We would like to determine if the alpha equals 0.05 level of significance if there is a difference in mean sports time per day between 7 to 11-year-old boys and girls. All right. So I am going to use my subscripts of B and G here for boys and girls. So I'm going to identify here what information do we have. So we've got 9 girls are sampled. So my sample size for girls is 9. My sample size for boys is 16. What's my next piece of information? The average for girls, X bar for girls, is going to be 2 hours per day. Oh, wait. 9 girls. Oh, yeah, 2 hours per day. And our sample size for boys is going to be 3.2 hours per day. Our standard deviation for the sample of girls that we saw was 0.866 hours. Our sample standard deviation for the boys that we sampled was exactly 1 right there. So here's the information that we'll need to compute all of our things of interest in this guy here. So we'll come back to reference that information. Let's go ahead and form our hypotheses, our test statistics, our p-value, all the good stuff here, all of our things in order. So our hypotheses. We believe that it is believed that boys and girls spend equal time playing sports each day. That's going to tell us our null hypothesis. Our null hypothesis is our statement of no change or no difference. If there's no difference, then it should be that the average time spent playing between boys and girls is equal. So I'm going to make an equal to statement here. On the other hand, our alternative hypothesis, let's see, a study is done to test this. It is believed that they spend equal time playing sports each day. A study is done to test this. So what I'm seeing here, let's see, determine at the alpha equal 0.05 level of significance if there is a difference in mean sports time per day. So it doesn't seem to me like anywhere in this paragraph it's been proposed to us that we think that it's a more than or a less than right here. It just says to us, is there a difference? And sort of the implied conclusion to that statement is, or not. Or is there not a difference? And so here, I think that my alternative hypothesis is just going to be my not equal to statement right here. Again, our scenario gives us no indication of which one is believed before the sample is taken to be the greater than or the less than right there. And I want to remind you of kind of one more thing right here that I know some of you are thinking. I know that what some of you are thinking is that in our sample, the boys' average seems to be quite a bit larger than the girls' average. But what you need to remember is the chronology of this. What timing ordering happens here? In all good science, the hypotheses come first. The sample is collected after the hypothesis. Our dilemma in a classroom environment is I need to just give you a paragraph that has the details that you need. But what you need to know is that as of the hypothesis determination stage right here, we haven't taken the sample yet. We don't have the information of these two different X bar values yet because we as scientists are still in the hypothesis phase of the science that's being done. We haven't moved on to step 2, which is perform the experiment and collect data. That's what would give us these sample averages right here. So remind yourself that when you're forming your null and alternative hypothesis, it is never appropriate for you to use any information about the samples that were collected when forming your hypotheses, because in real science, you don't have that information yet. Forming your hypothesis will always be something that's done before any data is collected. So never let your sample information, your sample average, your sample standard deviation, never let any details of your sample ever influence what you say about your null and alternative hypothesis. This should only be based on the verbal setup that's going on here, where I see things like determine if there is a difference in mean sports time per day. That's the only information that's relevant to my hypotheses because it has nothing to do with the sample data that was collected right here. Okay, so I'm looking at a not equal to here because in my statements, in my scenario, I never saw a suggestion that we believed that one group would have a greater or lesser average time than the other group. So we've got our null and alternative hypotheses here. Now we can go ahead and compute our test statistic. And the thing that I'm noticing for our test statistic here is that we need to compute a t-test statistic because we only have the standard deviation of the sample and we do have small sample sizes. So let me say here, since n1 plus n2 equals 9 plus 16 equals 25, which is less than 30, and we have S1 and S2, but not sigma 1 or sigma 2, we use T. So again, our choice between Z and T is determined by what type of standard deviation information do we have, how large is our sample size. Here we only have the sample's standard deviations, and we had very small overall sample sizes here. So we are going to use a T distribution to reflect that lack of information that we really have here. So what we need to do is we need to compute our test statistic, and to compute our p-value, we'll need to know that degree of freedom information here. So our t-test statistic is going to look just like our test statistic that we saw before. I guess I can call this girls and boys now. All right, and let's see what we're getting for our t-test statistic here. So what I'm seeing are some things like, notice right away again, we are claiming our null hypothesis says there is no difference between the two groups. So again, this will be 0. So it looks like I'm getting here. I've got my girls' average is 2 minus my boys' average of 3.2 minus 0, all divided by the square root of. The girls' standard deviation was the 0.866. We're squaring that, divided by the 9 girls that we sampled, plus We've got the 1 as the standard deviation for the boys sample. We're going to square that 1, but squaring 1 doesn't do anything. And we're going to divide that guy right there by 16. So we've got our standard error term here associated with our t-test statistic. Let's go over to our calculator and see what we're going to get here. And it looks like we're getting here our t-value. I've got a negative 1.2 up in the numerator. And down here in the denominator, what are we getting the square root of? I'm doing 0.866 squared divided by 9 plus 1 squared divided by 16. And I'm getting 0.1458. Okay. Oh my gosh. Oh my gosh. Calculator, help me out here today. Okay. So now I can go ahead and take a square root of this guy. I'm getting 0.3819. And doing my final division here. 3.142. So this still seems to me like a relatively extreme event right here that says that this observation, if the null hypothesis were true and there's no difference, then this is a relatively extreme observation. This is an observation that's a little bit more than 3 standard deviations below average. So let's go ahead and determine what our probabilities are that are associated with this. And let's remember 2 things that we're going to need associated with this p-value. One, we need to compute the degrees of freedom associated with the t-distribution. And 2 is a 2-tailed since our alternative hypothesis was a not equal to. Right. So let's go ahead and do these 2 things. I really need to compute my degrees of freedom first so that I can compute this probability. Stick with me here, keyboard. So I'm going to come back up to this thing up here and just grab this whole formula so I can reuse it. All right, so let's go ahead and fill this guy in here. I'm seeing here, I've got that S1 is the standard deviation for girls. Come on, you can do this, computer. Come on, stick with me. And that's my 0.866. Come on, 10. So I'm just trying to relate my 1s and 2s to my boys and girls here. I made 1 girls and 2 boys. So let's go ahead and compute this degrees of freedom term right here. It looks like up in the numerator, we're going to get S1 squared, 0.866 squared over 9 plus 1 squared over 16. And we're going to square that whole thing. All divided by, first thing here is 1 over 1 less than the first group's sample size. So that's going to be a 1 over 8. And then S1 squared over N1, that's going to be our 0.866 squared over 9 again, squared, plus 1 over 1 less than the other sample size, that's for the boys, so that's going to be 1 over 15. And this will be our 1 squared over 16, and we're squaring that as well. So I'm going to go ahead and compute this degrees of freedom term out here. I'm going to do numerator and denominator. Maybe I'll just do the 3 separate terms that we've got out there. So I've got here 0.866 squared divided by 9 plus 1/16, and I'm going to square that whole thing, 0.021266. On the bottom down there, I've got, let's see, a 0.866 squared divided by 9, square the whole thing, and then divided by 8. Ooh, tiny number. And same for the second one, 1/16 squared times 1/15, so dividing by 15 also. And I'm getting another tiny number down here. I'm getting 0.00260. So let's go ahead and do the addition in the denominator, do the division here. 0.021266 divided by the sum of 0.000868 plus 0.00026. And this is telling me 18.85 is the number of degrees of freedom that we should be using here. All right, so got to make a pretty careful trip to our calculator there. You should certainly compute some intermediary values. You definitely have to keep kind of a ton of decimals here. Notice if I chop this, if I try to round this to any fewer number of decimal places, we're losing kind of a lot of information. Don't cut yourself short on rounding right here. You're going to get wildly different answers if you round this a lot more than I did right there. You should be keeping like 5, 6 decimal places if you're getting these tiny, tiny numbers out there. So we're trying to compute our test, or our p-value, right? We've got our test statistic. We know now our number of degrees of freedom. So we're now thinking, get out of here, conclusion. Oh, we can't get rid of the conclusion because our keyboard doesn't work. I'm sure it'll come back to us here in a minute. Oh, what do you know? Moving later. So now in our t distribution, t sub 18.81 or 85 right there is our t distribution with 18.85 degrees of freedom. What we can see is that we were at 1, 2, 3, and then some. We had that t star was equal to negative 3.142 or something like that, right? So there's our t star location right there. We have a two-tailed test. And so we need to make sure that we capture the area in both tails. So to get one tails area, let's just go ahead and do our t dot dist. We're going to need to give it our t value in here. Let's come on over here. So we're going to do our equals t dot dist. I just want to remember, since I keep on giving wrong information in here, it wants first our value. That's our t value, the negative 3.142. It wants our number of degrees of freedom, which we calculated as 18.85. And it wants to know if it's cumulative or not, and we're going to say yes. And this is going to be equal to 0.002818. So to get two tails area, we can just go ahead and multiply that by 2, because we know that this is a symmetric distribution. So let's just multiply this number by 2 here. I'll just say equals 2 times B6 to multiply that guy by 2. And that's going to tell me 0.00564. Right, so So we computed our p-value associated with this hypothesis test. So now we have enough information that we can go ahead and form our conclusion. It looks like, so our p-value here looks like our p-value is less than alpha, and that should tell us to reject our null hypothesis. Now we want to be careful with our conclusion here. We do have a not equal to statement. So all we're doing is rejecting the null in favor of the alternative. So let's go ahead and say here, oh yeah, I can't type or can't, well, see if it'll let me. So what are we concluding here? I want to again caution you about the conclusion that we should be drawing here. Notice that in this case, in this sample, if we come way back up here, in this sample, we can see from our sample averages that in this case, we're seeing that the boys played sports outside, whatever we're measuring here, for 1.2 hours per day more than girls. But we are not trying to make some conclusion about whether boys play sports more than girls or not. Our alternative hypothesis is just there is a difference. We rejected the null in favor of the alternative. There are two competing hypotheses, and your conclusion has to be one of them. Since we've rejected the null hypothesis, we are going in favor of the alternative. The alternative does not say that boys play outside more than girls. I don't care if that's what this sample shows. That's not what our hypothesis was stating. Our hypothesis is stating there is a difference. That's it. So don't overstate what you know when you state your conclusions. When I'm stating this conclusion down here, all I'm going to state is the alternative hypothesis conclusion and conclude that there is a difference in mean sports time per day between boys and girls. So don't overstate what you think you know here. Again, recognizing that we're trying to make a conclusion that is either the null or the alternative hypothesis. Don't make a statement that's neither of those, such as boys seem to play sports more than girls. If that wasn't one of your two hypotheses, then it's not possible for that to be your conclusion. All right, so stick with what your alternative hypothesis is if you've rejected this guy here. If you've rejected the null hypothesis between so I'll appropriately hyphenate this to be actually specific here. 7 to 11-year-old boys and girls right there. All right. So the big difference that you should then see here for today is just that we have some new computation that we need to do. If we're in a t-test scenario, then you need to be able to use this kind of obnoxious formula to compute a number of degrees of freedom associated with your t-distribution. But other than that, there's not really too much that's really changed. Our structure is still the same thing. We're still going to start by stating some hypotheses. We're still going to follow that up by computing a test statistic. The test statistic components are even the same. It's our sample averages minus our population averages according to the null hypothesis divided by your standard error. That structure has been the same for every one of these that we've ever done. There's just more terms involved now to handle the fact that we're in a two-sample scenario here. Our p-value computations are exactly the same. The stuff I did over here in Excel today, you couldn't even tell that was from two-sample tests because I'd done the two-sampliness of it in the by hand parts here in my calculator, right? To compute the probabilities associated with our distributions, right? These pictures here, there's literally no difference whatsoever in what we've done last week. I guess the only tiny difference you could say is that our degrees of freedom now might not be a whole number because of the calculation that we're doing for degrees of freedom here instead, right? So relatively similar stuff here. Our calculations have been updated, but our concepts have not been drastically updated. What we're going to see in tomorrow's video, I'm going to scroll back up here. What we're going to see in tomorrow's video now, today we did these two scenarios. Tests for differences in population means with independent samples. In one case, we had a large enough sample that we could justify using the z distribution. In our second example, we had such a small sample size that we went with the t distribution instead, a little bit more appropriate when we have less information. In the next video, we're going to see our matched pairs examples here when we have dependent samples. Samples are dependent on one another. And we're also going to see our two sample tests for differences in population proportions. Hopefully you will agree that our next scenarios here are again going to be very, very similar to the stuff that we've already seen. We've got some different computation that we want to do in each of these two cases right here, but the concept overall and the structure overall and the process overall still hasn't really changed. It's just how do we now do the appropriate computations to handle the scenario that we've been provided here. So in our next video, we'll hit these other two out of the four scenarios, and that will be essentially all of the two sample comparisons that we want to be making here. Following that up in week 13, we're going to finally look at talking not about averages and proportions, but starting to perform tests for things other than just averages and proportions, such as performing hypothesis tests for a standard deviation or variance, as well as performing hypothesis tests for following a distribution. So rather than saying, where is this distribution centered? That's an average or a proportion. Rather than saying, how is this distribution spread out? That's a standard deviation. We're saying, what is the actual shape of the distribution? What is the distribution actually like? We can perform hypothesis tests for that as well to determine if something follows a certain distribution or not. With that type of stuff, we can ask questions like, is this a fair die or not? Do people take sick days evenly distributed across all days of the week or not? Stuff like that. So we'll see those coming up next week and the week after that here. So that's the wrap up for our first video this week. I'll hit the other two bullet points that are highlighted right here in our second video, and I will see you guys next time. Have a good one.